Hey everybody, Big Mac here. Welcome back to the final part of my favorite pre-calculus test questions. So this is the last video in a series that I've basically been going through the past couple months, just here and there, when I have time to make the slides and do a voiceover and stuff like that. Anyway, what are we doing in this particular set of videos? Well, again, these are just actual questions that I used on pre-calculus midterms. So these were for students who were taking a full semester of calculus, so it was covering all of the basic algebra and trigonometry things needed for a proper course in calculus. Again, assuming that students had the required skills up through Algebra 2 and geometry and stuff like that in order to start a college calculus class. Obviously, not all of those requirements were met, as I had seen in various midterms before, but I kept trying to emphasize some of those things throughout the semester. So that being said, this is the final exam, or the final midterm that we had before the final. So this was all just pure trigonometry stuff. So we talked about the unit circle. We had already talked about some right triangle stuff. So we also focused on the graphs of functions, the identities, all those famous things like sine squared theta plus cosine squared theta equals 1. Those kinds of things, as well as just applications of them and manipulations. So in this last midterm, I just had a couple extra questions. So, like before, I had some true-false questions. So again, just simple true or false. I did not require students to provide an explanation to the answer. I just asked them, is this thing true or false? So, our first one, if we had a value of x in between 0 and pi over 2, is it true that if you take the sine of the inverse tangent of x, then that's just the cosine of x? Is that a true thing? Second one, if we take the inverse cosine of root 3 over 2, is that in fact equal to 0.5235987756? Of course, our very last one, involving inverse trig functions as well. I had plenty of other questions as well that were true false, not just inverse trig functions, but the last one that I covered was, if you take the cosine of the inverse cosine of 5 pi over 4, you get back 5 pi over 4, right? True or false? Our second question on this midterm was basically a word problem involving multiple parts. So we're told that the temperature in degrees Fahrenheit on a hot day was modeled by this function. Our temperature as a function of t, lowercase t, can be given by 85 minus 15 times the cosine of pi over 8t, where I specify that t is the number of hours since 10 a.m. So when t equals 1, that's 8 a.m., when t equals 2, that's 9 a.m., etc. So I asked a few questions, and these were the ones that I thought were the most important. First question, what was the maximum temperature for the day, and at what time of day did it occur? So again, by time of day, I mean, was it like 9 o'clock, 10 o'clock, 5 o'clock? Specify if it was a.m. or p.m. Not just, when t equals 7, or when t equals 2.6. Something like that. Our second question involved, using our function and determining an actual value for when the temperature first hit 92 degrees Fahrenheit. I asked students to round to the nearest quarter hour. Lastly, our third part was, is this a good model to continue using into the night and into the next day? So I was hoping that students would look at the function and use some kind of quantitative support, either for or against the idea of continuing to use this model, even into the night and into the next day. So as a continuous function. So I was just hoping for some kind of an explanation as to why or why not would be a good idea. Anyway, let's go back to our first set of questions, our true-false ones. It turned out that all three of those were in fact false. So if you thought any of them were true, it's okay. We'll go through some of these in just a little bit more detail right now. But again, in fact, all three of these ones that I posted here were false. So let's look back at the first one. The first one, if you thought that the sine of the inverse tangent of x is the cosine of x, then we've got some problems, because obviously what I left as an option because some students still thought that the inverse function is just the reciprocal. And obviously by this point, if they didn't get it now, they weren't going to understand it, and they were going to have more difficult if they passed into the next course, which, again, some of them did, some of them did not. But some students saw this thing and they're like, okay, I know that tangent, or that inverse, they thought that inverse tangent was 1 over tangent. So then you had sine over tangent of x, and then somehow that magically transforms to cosine of x because they don't understand how functions work. And so, admittedly, I had a few people choose that would say that was a correct answer. So that being said, I didn't ask for the specific correct answer of this thing, just true or false, was it cosine, but we can figure out what this thing is in fact going to be. So, that being said, sine of inverse tangent of x, this inverse tangent of x has to be some angle, because you have to take sine of some angle. So, that being said, if there is such an angle, I'm just going to call it theta, such that the tangent of theta is x, or theta is the inverse tangent of x. Again, that's how we come up with our definitions for the inverse trig functions. So then if we have that our inverse tangent of x is just some angle theta, can we express sine of theta just in terms of either x or what other variables we had originally? So the easiest way to do this is to construct a right triangle. I specified that x had to be between 0 and pi over 2, just to make things super nice, everything was happy in the first quadrant, regardless of what you were thinking. So, that being said, if we know that the tangent of theta, drawing a right triangle, if we know that the tangent of theta is x, or we can write that as a fraction, x over 1, using our SOHCAHTOA method, so tangent being opposite over adjacent, so we could have x divided by 1, then if we have this right triangle going on, then we know from Pythagorean theorem, or just any of our other trig functions, that the hypotenuse has to have a length of square root of x squared plus 1, again, just from Pythagorean theorem. So then that being said, we know that sine of theta is opposite over hypotenuse, so we have x over the square root of x squared plus 1. But if we have sine of theta, and theta is the inverse tangent of x, then in fact, sine of inverse tangent of x is simply x over the square root of x squared plus 1. So that is rewriting your trig function just in terms of your original variable. And again, some people thought that this somehow, reduced down to a basic cosine function, which obviously was not the case, because cosine of x doesn't mean a whole lot in this case, because x is our side length argumentatively. For our second part, I asked if the inverse cosine of root 3 over 2 was 0.5235987756. So, that being said, the answer is false because the answer is pi over 6. The inverse cosine of root 3 over 2 is pi over 6. And that being said, I know that pi over 6 is approximately 0.52385, etc., etc., but they are not equal. Pi is not 3.14. Pi is an irrational number that goes on forever. Pi over 6 also goes on forever. So basically why I put this question in there was to see if students had actually, gone and memorized all of their cosine and their trig functions for going around the basic unit circle, as well for both your regular sine, cosine, tangent functions and their inverses, accounting for the fact that we have specific domains and ranges for our inverse functions as well. So that being said, if a student just shoved this into their calculator, saw that 0.52359, etc., and said it was true, well, they got the answer wrong, because I did not use approximation, I said equals. So, and I had emphasized that plenty of times in the course. One of the first things in class that I asked was, is pi equal to 3.14? Half the class still said yes, and after which I quickly corrected them. So that being said, the correct answer is exactly pi over 6, not this decimal equivalent. So last question involved inverse functions and inverses of inverse functions. So I asked if the cosine of the inverse cosine of 5 pi over 4 was just 5 pi over 4. Well, admittedly, normally when we do have inverse functions, you can take f inverse of f of x or f of f inverse of x, and you just spit back out the original value. This is true for most inverse functions, and that's part of the properties of inverse functions. That being said, though, that depends on your domains and ranges of your particular functions. If you have something simple like a nice linear equation, your domain and range are all real numbers. So there's no problem there. For trig functions, though, we have definite domains and ranges, especially since we have our multiplicities, with our trig functions as we go around the unit circle. So that being said, we do have to be more careful when something like this pops up. However, I hope that students, thought about what these things were actually representing piece by piece. And 5 pi over 4, that is a fraction that is definitely bigger than pi, so almost 4 in value. So you're asking me to take the inverse cosine of something like 4. Well, knowing our regular inverse cosine function, the input has to be between -1 and +1, because those are the extrema of the regular inverse cosine function. So that being said, inverse cosine of a number that's almost 4, it doesn't exist in the real number sense. So then if you take the cosine of a number that doesn't exist, you're still going to get something that doesn't exist. So that's why this one is in fact false. Because you cannot evaluate this, the piece that's inside the function here, inverse cosine of 5 pi over 4. On another version of the test, I had 2 different versions. I had also asked a slightly different question, and possibly a little bit harder. I asked if the inverse cosine of the cosine of 5 pi over 4 was equal to 5 pi over 4. And again, in that one, the answer is in fact false, because we have our issues about the unit circle and our domains and ranges for the inverse trig functions. Cosine of 5 pi over 4, oh, that's easy. You can compute that. That's definitely, what is it, -√2 over 2. That's not a problem. But then, if we were going to evaluate the inverse cosine of -√2 over 2, you don't get 5 pi over 4. By our default definitions, we get back to 3 pi over 4, because our inverse cosine function gives us a value between 0 and pi. So something in quadrant 1 or in quadrant 2 of our regular Cartesian plane. So even that one was still false. And again, admittedly, when you have nice happy functions, we don't have to worry about those kinds of properties, but if for a trig function, we do have to be a little bit more careful. So how did students do on these 3 true-false questions? Well, basically, it was a situation of, if they did well at the beginning of the course, they were still going to do well in this bit of the course. If they messed up at the beginning, like they didn't understand inverse functions and stuff like that, they were still going to have issues with the inverse trig functions. So yes, I make these tests a little bit intentionally review, because there's a whole semester's worth of things that I am testing on. So I try to, try to subtly make every midterm a cumulative exam, even if we're just focusing on specific parts. So that being said, I asked students. I should have put this in the superscript by accident. Sorry about that. But a lot of students, were going through that problem, and they actually worked it out with the right triangle. Although they had the square and not the square root in the denominator of their answer. So even if I had made this like a multiple choice question, I could have made that one of the answers, and I probably would have gotten, a lot of students would have gotten that wrong still. But it was good to see that they were following the right track, for sure, even if they still didn't know their Pythagorean theorem as well as I hope they did. Going on to the second question. Second question. Here we go. So our second question, again, we had our temperature model for a hot day. We had 85 minus 15 cosine of pi over AT. We had 3 questions. What was the max temp and when did it occur? When did it hit 92 degrees for the first time? And is this a good model to continue using? So I broke this up into 3 parts as well. There we go. There it is. Okay. So when we have these kinds of trig functions, and admittedly we could graph these things as well, students had their calculators. So if they wanted to, they could just graph this thing out and figure out what's going on. But generally these things are written in the form of y equals c plus a cosine of bx, or c plus a sine of bx, where your value of a could be positive or negative, likewise for c. But we know just based on a couple of these values some specific qualitative things about the function as well. So for example, our vertical shift, which is just c, which is the number in front of our function. So that is just how much we are going to raise or lower our function in the y-axis compared to our regular function. And then also, we know that this value, this vertical shift, is the average value of the function over one complete period, because basically this is your midline through your particular trig function, through your sine function or cosine function. So for every point that's above it, you've got another piece or another part on that period, within that period, that is below it. So they all just kind of, even out, and you end up just at this middle line C. So we also know that the absolute value of a, because this could be a positive or negative value, but we take its absolute value and we call that the amplitude, which is just basically the maximum distance away from the center. So if you want to figure out what the minimum is, you can relate that in terms of c and your amplitude. If you want to find your maximum value of the function, you can relate that in terms of c and your amplitude. Our coefficient b is obviously going to affect how our function behaves in the horizontal direction. So obviously students think of this as a horizontal stretch or horizontal compression. So the useful formula in terms of drawing these things that we talk about with students is if you take 2 pi and then divide it by that value b, you get the period of the function, which is how long it takes for, the graph to complete itself in one complete cycle. So from there, you can obviously figure out what the graph is. You can figure out your max and mins and everything else like that. So these are some basic information that I hope students were able to read off from the equation and use that to help answer their questions. So for part A, what was the maximum temperature? Well, like I mentioned, we can relate that in terms of our vertical shift c and our amplitude a, or absolute value of a. So we know we have the absolute value of negative 15 just because positive 15, plus our 85. So our maximum temperature for the day is going to be 85 plus 15, or 100 degrees Fahrenheit. So that being said, looking at the graph itself, we have 85 minus 15 cosine. So what that tells us is our graph is actually going to start at the bottom, climb up to the top, and then it's going to complete its period back at the bottom, because we have our negative 15 coefficient right here. So that being said, we needed to figure out what our period is to figure out when is that maximum going to be. So, again, going through the graph, we know that it reaches the maximum temperature halfway through. So our period, we can evaluate that by plugging in b equals pi over 8 into the period formula. So we have 2 pi over 8, so that becomes 16 hours. So that tells us that our period is 16 hours long, so halfway through that would be 8 hours. So then we went from our minimum to our maximum within a period of 8, or within a time span of 8 hours. So 8 hours after 7 a.m., you go 8, 9, 10, 11, 12, 1, 2, 3 p.m. So that was the answer I was looking for part A. I did not need a whole lot of explanation. Obviously some students just used their calculators and graphed it, and I was okay with that part. As long as they understood where everything was coming from, how they were coming up with each of their answers in particular. Part B, I did require students to show their work on, because this was a bit more computationally expensive. So obviously they could still use their calculators to help on a little bit, but the question was, when did the temperature hit 92 degrees? Well, we have our temperature function in terms of our time in lowercase t. We'll just set that equal to 92 and see what happens. So first we need to get our cosine function all by itself first. So you subtract 85, 92 minus 85 is 7. You then divide everything by negative 15. So on the left side you now have negative 7 over 15 equaling the cosine of pi over 8t. So now to get rid of this cosine function and try and isolate t by itself, we need to take the inverse cosine, or the arc cosine, of the value. So we now have the arc cosine of negative 7 over 15 is equal to pi over 8t. That being said, again, I expected students to use their calculators, so they could compute the inverse cosine of negative 7 over 15, and they should have gotten about 2.06 in their calculators. So that being said, to get t by itself, we just multiply this particular number by the reciprocal of pi over 8, which is 8 over pi. So we get 8 over pi times the inverse cosine of negative 7/15, and that's going to come out to about 5.236 hours. So that being said, that was the particular value of t we were looking for. And again, if students used the graph, they could verify that as well. But I needed the students to show their work, at least on to this level of extent, to explain to me that I know where this answer is coming from. So in terms of relating this back to the time, well, 5.236, that's about 5 1/4. So 5 1/4 hours, 5.25. So 5 1/4 hours after 7 a.m., you got 8, 9, 10, 11, 12, and then 1/4 hours, of course, 15 minutes, so the time would be about 12:15. Now, admittedly, some students got freaked out because they're like, wait, I just plugged this in, but I know that there could be another answer for our inverse cosine function, but they realized that it's before 3, that our time that we found was 12:15 before 3 p.m. So yeah, this is the first time that it occurs. Naturally, it also occurs after 3 p.m. in the afternoon, once the temperature starts coming back down. And wrapping up our discussion, we had part C. We were asking, is this model a good one to continue using into the night and throughout the next day? So again, I asked students to explain why or why not, and admittedly, there were a couple of answers that I was pretty lenient on. The one in particular that I was hoping people would write was, after they realized, well, the period of this function, which is supposed to model your daily weather, it's only 16 hours long. A day is 24 hours, so then it's not going to be a good model because the function is going to start repeating itself earlier than the actual day will. So that being said, if we just let this function continue on, the next time, according to the function, that it will hit 100 degrees will be the next morning at 7 a.m., which, granted, given some geographical bias, that still is super unreasonable. But then that would also mean that it dips back down to like 70 degrees at 3 p.m. the next day, and then gets back to 100 at 1 a.m. in the morning? Yeah, it just makes no sense at all. So that's why this function does not make sense to work out throughout the rest of the time. So that being said, how did students do on these particular sets of questions? Pretty well, admittedly. So, part A went very well, and part C was okay. Again, I was kind of lenient on how students did, or how students tried to describe things. Admittedly, some of them tried to go more worldly, like, obviously the weather pattern will change the next day, so this will no longer be a good function. I had some students who were like, yeah, as long as you stop the function at 1 a.m. and then you continue it, and then you start it back up again at 7 a.m. So, again, I was getting a couple weird answers, but for the most part, I was pretty lenient on that. So, a weird thing that happened, I don't know, I understand why it happened, it's just kind of weird to me. So, on part B, where I was asking what time did it hit 92 degrees, a lot of students wrote down that the time was 12:24. Which, if you would then round to the nearest quarter hour, would be 12:30. So, where did they come up with 12:24 as the time? Well, if you've got 5.23 or 5.24 hours, a lot of students, for some reason, was like, okay, so 5 hours would be 12 o'clock, and then 24 minutes afterwards, because that's 0.24 hours, totally forgetting that there are 60 minutes in an hour. It's okay. It happens sometimes. I wasn't too mean on that. Or, admittedly, some students were just like, I have no idea what to do. I am so screwed for this final. And admittedly, some of them were. But that's beside the point. But again, students had their calculators on this last question, so for the most part, it went pretty well. That being said, there was a question that I asked that I hadn't mentioned yet. Because I intended this to be just like a quick little, 1 point, 2 point... quick thing, do you remember your definitions type question. So going back to our function here, I asked, what was the average temperature over the course of one period? So, in my head, the student should have thought, oh, well, if it's the average value over the course of one period, that's just the vertical shift. The answer is 85. Done. What wound up happening was I saw students trying to plot it hour by hour and calculating it and wasting so much time that I did not expect that to happen. So, and admittedly they still got the wrong answer because either they rounded wrong or they included a data point twice because most of them had 25 data points that they were listing. So that messed things up a little bit. Anyway, thank you guys so much for watching these series of videos. I'll try and combine everything into one nice cohesive bit right now. Sorry this came out in two parts as second part here at the very end, but I will continue to do some various math videos throughout the year, especially now that I do have a math teaching job, and I am looking forward to that. So until next time, this is Big Mac saying, later.